Introduce Martin Wiemann. He's going to present his latest work on the combined method approach for NanoBioDetect, for the NanoBioDetect project. You have 15 minutes.
Yeah.
The floor is yours.
Okay. So hello, everybody. I'd like to thank the organizers for inviting me and giving the opportunity to present some of our data which have been collected in the NanoBioDetect project. So I don't want to sell anything to you. I just want to present some of our methods which I've found useful even in biomedicine, although I must confess that I'm more or less a toxicologist. So to start with, the major aim of the NanoBio project was to detect and quantify nanoparticles in tissue sections and also the identification of the nanoparticle containing cell type, because we believe it's worthwhile to look at or to ask which cell contains how much nanoparticles, especially for the reason to construct new in vitro models. And on the way to achieve that, we used several more or less modern techniques. So the first I would like to talk about is the enhanced dark field microscopy, the DFM, and combined with the hyperspectral microscopy. The second one is the laser ablation inductively coupled plasma mass spectrometry, which is LACPMS, which is a nice method to be combined with light microscopic detection and others. The third one is the time of flight secondary ion mass spectrometry, TOF-SIMS, which we show combined with light microscopy data and also with ion beam microscopy data. And last but not least, short glimpse on what is possible with MALDI-MS, so matrix-assisted laser desorption ion mass spectrometry imaging, which is not well suited to detect nanoparticles, but it's nice to look at metabolic changes in tissues. So to start with the DFM, so this is what one is perhaps used, maybe some of you in the audience are using dark field microscopy. It's quite common. This is a section of a lung which has been intratracheally instilled with gold nanoparticles, which are sized 30 nanometers. And this is a typical image you see under a dark field microscope. Very beautiful gold shaped or small golden particles. Maybe they are also red or other colors, because gold and other metals like silver, they exhibit a plasmonic resonance and they appear as colored particles. And this is just for comparison, because of course you can do electron microscopy on all these samples and you can detect single particles here in a macrophage, which is not the same cell but would be equivalent situation. Here you see single particles which might correspond not to the yellow ones, but perhaps the single would correspond to the small blue ones, so just detectable at a size of 30 nanometers. In fact, I would say 20 nanometer, this is the lower threshold, and smaller particles can't be detected with the dark field microscopy. So you can get information out of the light which is scattered here. As I just said, plasmonic resonance gives you colored particles, but also metal oxide particles can be detected. And we come to the hyperspectral imaging. So if the light is analyzed for those spectra which are generated, so the particles are illuminated with bright white light, and you get a spectrum from each of these particles, you can analyze these curves here, and you can do a hyperspectral analysis, and you can collect a bibliography of these curves and compare known and unknown samples. And this allows you to detect, for instance, as is shown here, or to differentiate. This is an example in which we analyzed serum oxide particles here in a lung, within lung macrophages. And these are curves simply taken from a tissue. It looks not exactly the same, so you can see here the difference. These spectra are not very characteristic. So this is the reason why you always have to know in your sample there are some particles which are really, in this case, serum oxide, and then you are confronted with particles you don't know which type they are, and you can compare these libraries here from these spectra and can allocate the right spectra and can identify these particles. This is quite nice. We were a bit disappointed because we are not able to use libraries which are generated from particles which are made on slides, just taken off from, and not in a tissue, just the slides dried on surface and so on, generate a library. And this didn't really work very well. Another other experiment, an example. Just the question, what can be done with this? This is from cells which were lavaged from a lung, and the lung is, and the animal has been instilled with silver particles. And you can see macrophages like this, and here these neutrophilic cells. And yeah, this was a versatile method to demonstrate that there was silver here around and also within the neutrophils. Because most people believe, and so did I when we started with these things, that just the macrophage take up all these particles, but you can detect very reliable also in the neutrophils, and this is true not also for silver. We have found this also in zirconium-loaded lungs. And this is a nice example of how this hyperspectral microscopy can be used in toxicology and probably also in biomedicine. So to sum up this part, so the DFM is a valuable tool to screen tissue sections. And this is always an issue, because if you are going on to high-resolution techniques, you have also only the capability to analyze very small sections. So you have to provide an overview if you are looking at a complete section. This can easily be done with a DFM, and in part also with a hyperspectral microscopy, which may be used to identify these particles simply by means of comparison and comparing these spectra. So coming to the next technique, which is the LACPMS. Maybe some of you are familiar with this technique. So make it short, there is a laser which is focused on a sample and into an ablation chamber, and here you must imagine is a section. Usually we are working with cryosections, maybe also you can use fixed tissue. And there's a stream of helium which is floated over the sample, and here a plasma is generated, and this is provided to the mass spectrometer. And the resolution, of course, depends on the size of the laser beam. So this may be 50 micrometer, maybe smaller, down to 1 micrometer. But of course, the mass you are converting into a plasma is going down, the smaller it is. But in principle, you can achieve resolutions of up to 1 micrometer. And what is quite nice about this technique, you can calibrate it. If you have a sample, for instance, if you have gold particles, or you have silver, for instance, or can solute a salt within a gelatin matrices, you can generate so-called matrix-matched standards, which have the precise thickness of your section. Then you can do such a calibration curve, and this is quite exact and it's quite linear. And this is really an amazing technique to do quantitative measurements right in a section. Furthermore, it is possible, if you are manipulating the technique a little bit and go to longer dwell times and make your measurements a little longer, then you are able to identify single particles, in this case gold particles. So this is a calibration distribution for gold particles sized 30 nanometers, and you typically end up with such a distribution. And if the particles have a diameter of 50 nanometer, you must see these numbers here. This is 12,000 and this is 50,000 here. You have another distribution. You can distinguish between small and large gold nanoparticles in a single particle mode. This is possible. And this is quite nice. This is just an example we have finished in the last year. This is a spleen section from an animal which had received these gold particles via intratracheal instillation to the lung, and these particles were distributed over the blood flow and reached peripheral organs. And you can see here a section of the spleen, and then it's also analyzed the distribution of iron to distinguish between the red and the white pulp, and you can see nicely the distribution where the particles are located and if there is a preference for any size. I won't go into the details here. It's just an example to show that it's possible to allocate these particles depending on their size in tissue sections on a single particle mode. Furthermore, the technique can nicely be linked up with immunocytochemistry. This is just one example of macrophages. We've heard about the marker CD68. This is a macrophage marker, and this is a lung which had been intratracheally instilled with silver nanoparticles. And these are just the immunocytochemically stained green dots with a bit of autofluorescence in the background. These are the macrophages, and this is a secondary antibody, so this is common immunocytochemistry. This is nothing new. But if you add a second antibody, which is gold labeled, 10 nanometer in this case, and you can do this and have a sort of a co-labeling, and then you have, as expected here, in some of these cells, you are expecting to find silver and also the gold signal. And by this, you can make it compatible with the analysis for silver and gold, for simultaneous analysis of silver and gold. And this is what is shown here. You have the gold signal, which is more or less equivalent to the immunocytochemical staining, gives you also an impression of the resolution, which is, I mean, this is what you can achieve on a light microscope. This is what you can achieve at a 10 micrometer resolution with the LACPMS instrument. This is the distribution of a silver, and this is the overlay demonstrating that most of the silver inside the macrophage is really inside macrophage, and it's co-localized with the macrophage label. So this is quite nice because it's a universal technique. You can combine this with any antigen you can label and think of. You can do co-labelings, and you can also use lanthanides and other things to label and do a labeling of a multi-labeling of up to 4 or 5 antigens at the same time. This is possible. Of course, it takes time, and this is not it's not really a cheap method, so you have to go for it. Finally, with the LACPMS, it's possible. This is one example from the lymph node, again, an animal which has been instilled with silver into the lungs, and the silver is distributed, as I told before, over the bloodstream, and here it reaches the lymph node, and there are some particles here, right, and samples in the lymph, in the depth of the lymph node, which can be also stained with the autoradiographic method and also with dark field microscopy, just to make sure that they have, in a single, in an isolated situation like here, there is some concentrated occurrence of silver. Because if you want to go for the question how much silver is inside this single cell, and you know that the laser beam is too large, you may have to make sure that when you're going for a laser field like this, that you have just one cell inside. And we have done this and went through all these calculations, which are shown here in this publication. But we ended up with a note that about 3.5 picogram of silver was roughly in that cell. This is an estimation, of course, and as shown here, there is a lot of dynamic within these measurements, and if you would take such a high peak here, you end up to 140 picograms per cell. So LACPMS is quantitative. A single particle is possible. You have a lateral resolution down to 2 micrometer, 1 micrometer, depends, and it's combinable with DFM-Haze and immunocytochemistry and so on. So the third approach was the TOF-SIMS as a tool in nanomedicine. TOF-SIMS is a technique in which ions are bombarding the surface, and it has what you analyze are these ions which are released, secondary ions. A technique which has in the last instrument version and resolution, lateral resolution of less than 35 nanometers and a very high mass resolution meanwhile. And in the project, we compared this with what is achievable with the IBM, the ion beam microscope. If you ever been in front of such a microscope, it's really a huge instrument, about 10 meters long, and there are protons bombarding these sections, and you are analyzing the X-ray and so on. But if you compare this with respect to sulfur, phosphorus, and in this case zirconium, you find this is what is the outcome with the IBM, and this is what is the outcome with the TOF-SIMS. So you see more at the same place, and by the way, this is the same site which has been analyzed primarily with the IBM, and after that with the TOF-SIMS. So there you can see more places with zirconium. So the resolution is higher, in fact. it's better you see more and in more places. So I would recommend in that case to go for such an instrument if you really want to see where are small particles located. And which is also nice about this technique, it can be combined, of course, with the analysis of the release of organic methods, as it's shown here. Again, a lung instilled with silica in that case, paramagnetic particles with a silica coat. And what was important for me is to look for the phosphatidyl shoreline, which can be analyzed due to a fragment which is 184 in mass. And what you see here is that the silica particles are not covered with the phosphatidyl shoreline, which is a major part of the lung surfactant and so on, because all people have been thinking that this is the case, but actually it's not, and this is within a quite recent paper. And this is my last slide, just to give a glimpse what is possible with the MALDI-MS technique. There is a poster number 97 if you are interested in MALDI-MS and the possibilities to analyze lipids in the lung. As I told you at the beginning, this is not a technique to go for the nanoparticles, but to go for the lipid differences, which in this case had been elicited in the presence of nanoparticles. If you want, I can explain it to you on a poster. This is for all the people who did the work, thanks to them, and I'd like to thank you for your attention.
Thank you very much, Martin. Since we are slightly behind time, we take all the questions as for Hans later.